Actually didn't prepare.
Oops. Okay. Yeah, recording. Today, just for the recording, today we're just doing an overview of interesting work that we saw at conferences 2 weeks ago. ICML, and I was at IJCNN. So IJCNN, for those from Albuquerque, this is San Antonio Basilica. So San Antonio is near and dear from everyone from New Mexico, and like every second street is San Antonio Street or something. So that's where it comes from Padua in Italy. Great, fantastic. So there was one interesting poster there by a theoretician that is called Turing computation with neural network composed of simple rings. Cryptic name, but basically it's a binary neural network that can model Turing machine, and it's not the recurrent neural network, but Turing machine with a limitation. Tape is not infinite, finite tape. So it's not a universal Turing machine, but it's a computer. But the point, the interesting point, let me give you a spoiler to another poster. The interesting point, this is like almost a SynFi ring, like a ring of nodes that just, this layer affects that layer. Imagine you took an MLP that has the same size of layers and put it on itself. So that's a ring of activity.
So how is that not recurrent? Is it not cyclic?
It is cyclic. It's a cycle. Yes.
Okay, yeah.
So this person, Jeremy, had a proof in a previous publication that this a network composed of those cycles can model any finite finite state machine, basically finite automata. That's not a surprise, I guess. But here he shows the Turing machine theoretically can be modeled, and what he shows, because I wasn't like Farfalla, I couldn't do what she did. I just put it on my website. So here's a computation. See how it's basically like Enigma machine, the gears. So they do rotate some activity and pass this activity to, like he's done all of that theoretical construction. This is not a trainable network. He just demonstrated theoretically that binary network, from a binary network, you can construct anything that a Turing machine with finite tape, any length finite tape, but still can do. And that's an interesting, all the recurrence is interesting to me. But while I was marveling at his poster, was like, well, what is really going on, how it works? A guy stops by, and this guy says, did you know that a fruit fly has a SynFi ring just like that in the brain? And he shared this video with me there at Johns Hopkins. So this ring, this knot at the bottom, is actually a ring of neurons alive, and what it does a compass. The activity travels in that ring depending on the direction. It's kind of like a compass, but it's more of an accelerometer compass. It's not a universally connected, it's connected to the body system. So it's more of a local thing. I was like, wow, I never heard of it. And he's like, oh, this kind of ring system for the compass part is quite common in many insects, at least. And I left this here. I don't want to play because I want to leave room for Alex and Mahfuz for there. But he has a paper where, well, continuous state estimation. And actually, even those binary switching maps are similar to that previous paper where Jeremy is demonstrating how he can prove that a collection of those SynFi rings is equivalent to Turing machine. And I was telling him, why don't you make it trainable by using implicit differentiation? Maybe it's a fixed point differentiation loop. So that's a conversation we had. Another relevant part or interesting part, it comes to the paper that Alex shared, and that's going to make made a splash that we are very dependent on hardware in which methods become successful, which are not. Somebody took 100 plus different methods, model training. It's a meta-analysis, and divided our computation growth into eras, pre-deep learning, deep learning, and now we're entering large scale era, and there is some flattening. There is a jump. So on the right, you see this whole plot from 1952 to now. And on the left, you see just the deep learning era where it kind of, the slope changed, it started to grow faster. But then with the scaling law, when big companies, I guess, felt some blood, they threw momentarily, like instantaneously, a lot of hardware. So there is a jump, but then the slope is lower. So it's kind of saturation. I found this interesting. So that's from the paper I cited. Another thing is for some of that is for William and Yarong is busy now with some personal stuff. But anyways, so the desire here is like retinotopy. So from retinal images, people are trying to construct what the person is seeing. But this is from fMRI. Collect fMRI of a person looking at an image and try to reconstruct an actual image or what was the person looking at using a GAN. And some of the results, of course, training results are slightly better than testing results, but still interesting what they're getting with a GAN. I don't know how, it's very hard, like how much leakage is there or is there any leakage, but it's interesting. It kind of reconstructs the field.
They're only using fMRI.
Yeah, they're like this fMRI activity. So fMRI is the only input for that. So then, well, they train a GAN, so it's all fantasized by a GAN, but pretty interesting. So Big Brother is watching us. Be careful, especially when you go to fMRI scanner. Yeah. Okay, now I did not find a picture. There was one poster that I remember vividly taking a picture of.
Can I ask you
What is it? Yeah, split training for that. We'll
You sent it
kind
to
of
me, I thought,
discuss.
yeah.
Oh yeah, I thought, but I couldn't find. Okay, well, anyways. So ICML now. Who starts first? Who can? Oh, I will change the slides. So you just come on.
Can I ask you what the previous?
Okay, whose slide is that?
I actually took this slide. Yeah, I uploaded this slide. I actually found this one interesting because for a while, maybe 1 year or so, I have been working on different explainability things of machine learning models, but I didn't come up with any interpretability models or tools that actually focus on clustering things. So I found this one interesting because this one is actually dealing with unsupervised models. For supervised case, we know how to deal with these problems because when we give an input, it actually maps to a set of probability scores, and we know that what does each probability means here, because each probability is associated with a particular class. But for unsupervised models, if we map an input to an embedding space, so how to deal with that that kind of unsupervised interpretability, how to interpret in the embedding space. So I found this one interesting, but I actually didn't look into the details of the paper. So I am not now able to say the broader or general idea they have used for these, but this one might be interesting.
Yeah. Next. Hey.
Yeah. Yeah, I put this slide too. So I found this one interesting because this one is basically related to continual learning For example, traditionally what we do, we actually build a model specific to a task. And for separate tasks, we forget the earlier model and train afresh and build a second model for the second task. But this one is quite different and very much related to how people learn over multiple tasks so that they don't forget the earlier task. And this one is basically a computer vision task, but inspired from neuroscience, how people learn over multiple tasks and can equally perform or acceptably perform well over all the tasks. So to bring this idea into artificial intelligence, they have actually proposed a scheme so that we can train a single model over multiple computer vision tasks, for example, or it could be different other tasks, so that it can perform well on multiple tasks. Yeah, I actually didn't go into the details because I didn't get a chance to look into the papers in detail. But this is the main idea, that how a general model can learn multiple things in continual fashion, so that it does not have to start afresh for each task, and ultimately it can perform equally or reasonably well over all the tasks.
It's very similar to Renaissance method, but it does this rewiring, which is interesting. Wonder how they make sure it maintains some level of sparsity when they add the rewiring in.
Mm-hmm.
Yeah, I need to send that paper to the SN.
Yeah, it's basically the first part is almost exactly its method.
Yeah. Wait a second. But the concept is all we need, Mahfuz, so don't worry. What is the concept here?
Okay, this is actually data models. I found this one interesting because this one actually analyzes the aspects of training data on the ultimate trained model. That means what parts of the training data, if used to train the model, what would be the prediction score, for example, for a target sample without training it afresh. That means they have used a surrogate model to conceptualize or to get the idea or to get the results of the original model based on what portions of the training data were used to train the original model. For example, F is the original model and X is a target sample, and S prime here is the parts of the training data used to train our model F. So it actually captures the effects of which samples from the training data has how much contribution to the output score. And they have shown that analyzing the effects of the training data based on surrogate model, it could be used for different use cases. For example, it could be used to generate counterfactual explanations, and it could be used for other cases, for example, database embedding and similarity measures. So I found this one interesting because without training, it can identify the effects of training data.
One comment here. So it would have been, I heard that idea from a friend long ago, and I was like, but yeah, we're getting there. It would have been good eventually to have a way to look at the data set and an architecture without training, be able to say, will that architecture work on this data set?
Yeah, something like that.
Yeah. Then you can do architecture optimization without actual training. And if it's at all possible. We could sort of assess those in animals by energy constraints and things like that. Like, will this animal be cognitive? But we know a lot about animal brains and things like that. But that would be cool if we could do that. Yeah, that's a cool choice. Okay.
Okay, this one I actually found interesting because we have been working on contrastive learning for time series representation. And we know that for image data, we can use multiple augmented view of the data for contrastive learning. But for time series, we actually don't have any particular idea how to create different views of the same data for contrastive learning. So the idea here is that instead of using our ad hoc nature of augmentation of the time series data for contrastive learning, maybe we could incorporate some expert features for our contrastive learning for time series data. And they have said usually time series data comes up with some expert features inherently, so that we could use those concepts during contrastive learning, so that similar time series can be kept close to each other, and very dissimilar time series can be pushed apart from each other based on expert features. That's the main idea.
Any comments?
This one is actually a modification of it is particularly related to model interpretability, and they actually proposed a model interpretability technique based on some sort of optimization formulation without and they don't need to, for its evaluation, it does not need to model retraining like ROAR or RAR or similar kind of things. It does not require any model retraining, and it actually used the similar concept of ROAR to formulate that optimization problem. But I didn't look into the details of the paper.
Yeah, well, besides that, they took, they were inspired by Noah's ICHI first title, clearly. But yeah, that's an interesting work.
Wait, do you know the details of it?
No, that's the first time I see it.
Because I can't read that.
Did you read it?
No.
It's an ICML paper, and the slides are available to everyone. So,
Is this
thanks for inserting link to the paper.
Yeah.
Yeah, that's very helpful. It's online. I'll post it. Cool.
Oh, okay. This one is geometric contrastive representation learning. Especially the main focus is multimodal. Multimodal contrastive representation learning. That means the idea is if we use multiple modality, for example, here the image and the corresponding each page, so that in the embedding space, they can be treated separately. That means the textual portion of the data, the image modality of the data will correspond to some embedding portion in the embedding space, and the speech modality will correspond to some other part of the embedding space, and they will not interfere with each other in the testing setting. For example, in the testing setting, if one modality is missing, it will not bother the embedding space. It will perform as well. That is the idea. That means it is creating three space. For three space means for each modality, for example, there are two modalities here. For each modality, one embedding, and they are creating a combined embedding. And for the testing setting, if
In a row and-
any of the modality is missing, then it will perform as well. Maybe I found this one interesting because we use different modalities for our data, for example, fMRI, SMRI, or for some gene data. And maybe we could incorporate all of these modalities to create a separable embedding space.
This would be interesting to apply to our multi-encoder problems. We were saying was the embeddings were just overlapping, and we weren't able to leverage any kind of useful information between multiple sites.
Yeah. That's interesting. Yeah, thanks.
Mhm. And this one is actually for model debugging, using two things. They have used the one terminology called concept activation vectors, and another one is counterfactual explanations. They have used these two ideas, two tools to say why a particular model is making wrong decision. What is the reason? For example, the zebra could be identified as a tiger because of the stripes, something like that. That means they are incorporating the concept activation vectors, and they are using counterfactual explanations to identify why a model has made mistakes in their predictions.
Yeah, like I saw a similar tutorial talk at IJCNN when the authors don't overlap from Arizona State that we can learn parts of the concepts and things like that. I don't know, where do you take the data about the
That's
concepts?
what I was gonna say. It's like, this just sounds like a more data question. It doesn't seem that interesting. Otherwise.
Yeah, I don't know.
Yeah, so if we have an image data set that has a bunch of labels and stuff, that's great. You could do anything with it, but it'd be more interesting to maybe work from existing limited data sets to try to combine them and do this kind of work.
Well, there people were cutting out segmentation first and then labeling the segments
Exactly, yeah.
manually again.
Yeah.
Okay, well, another one, Noah, just for you.
Yeah, so this one is actually very much related to saliency methods, related to model interpretability. How can we verify, how can we test that our interpretability methods are consistently providing reasonable reasons for model predictions or not? And they have actually created a ground truth based evaluation framework so that we can identify whether the models are making prediction based on the correct reasons or for the wrong reasons.
That's an old thing though.
I was gonna say,
I mean, even I've done that.
I've done not.
Um,
I'm always doing
seeing
things
some of these
for wrong
posters,
reasons.
I'm more and more convinced that getting into these conferences is a gamble. Honestly.
Here's the secret. I think the
Mm.
like sub conferences.
Not just gamble, you have to feel, it is like gambling, it's like a market.
Yeah.
You have to feel where the crowd is going and like, yeah, you want to. Whose slide is that? Tutorials. Mahfuz, is yours or?
No,
is
it is not mine. Maybe it is
Yeah,
from Alex.
it's mine, yeah.
Yeah, can you take over,
Uh,
Alex?
Yeah, can you hear me? Okay. So it's like some two tutorials I like it. This one is on basically validity, reliability, and significance. And I think this is important part that we have to like use in our evaluation of the methods. Like for example, we run multiple models, we have different hyperparameters. And in this tutorial, they introduced a linear mixed effect model that can allow check the significance of the hyperparameter in the result. And I think, and they have like this book, and it's a free PDF on their website. And I think it's a good read for us. So we can go next slide. So I found there have been tutorial on causality and deep learning. It was interesting because first they just give some background on causality and DL, and then they talk about how deep learning can be useful for causality and how causality can be useful for deep learning. They also talk about human causal learning. I think the main interesting part of it, it was how we can like connect causality to deep learning, and how we can make statistical models that kind of include interventions. And when we include the interventions, we kind of define new joint distributions like that should explain better the data or phenomena. And for example, we can have a like if you have a cow, like and we have different background, some cases will be kind of very not normal, like we usually think about cow on the grass, but cow can be on the beach in and we want kind of model understands the scene. For example, if you want to recognize object on the scene, and if you can use like intervention, maybe we can improve our models. So this tutorial is actually very long, and I think most of it was related to reinforcement learning, but it will be interesting to understand how we can like merge causality into like representation learning. And for example, intervention could be like maybe we can consider some attributes of the medical data, like attributes of the subjects, or like maybe like introduce like intervention to the data itself. So this is the idea. We can go to next slide. So this is like not very big like paper I found, but there is a technique called label smoothing, and it usually kind of positive label smoothing, and here they introduce like negative label smoothing. So for example, instead of giving a target like one hot vector, in label smoothing we put kind of Gaussian over the label, and we have not like one hot encoding vector, we have like smoothed version of it. Like if we have like 0, 1, 0, we can have 0, 1, 0, 8, and 0, 1. And here they introduce like negative smoothing, where, for example, you put minus 0, 1 and increase the correct label to 1.2, and you also have like minus 0, 1 just to balance it. As they showing how like this negative label smoothing can help in some cases and how it improves confidence of the models. I think it's like small simple trick, but it might help in cases where we have like noisy labels, and they try to like justify it theoretically by like relating this approach to label noising learning. I think one of our like lab person, like in the lab, I think works on this topic where we learn with noisy labels. We can go to the next slide. So there is some papers on transfer multitask learning. In this paper is what's interesting because it tries to deal with like multitask learning as a like multi-objective optimization. And they show how they can find like better solutions that on Pareto surface, like that is Pareto optimal. And they're showing it works better than previous methods. And I think in a lot of cases, for example, in my research, I deal with multi-objective optimization. So I wanted to learn about this more and try different methods. And that's why I think I found this interesting. We can go to the next slide. So there is a paper, it's not actually like very big, but it's more like a trick when we pre-train the model and we usually do like transfer learning. And when we do transfer learning, we usually use linear projection or we fine-tune model to the task. Here they suggest you can use all the features of your neural network and run, for example, group lasso to find features that are most predictive to your task. And this way you can improve your performance better than just fine-tuning. It's a like small trick that kind of allows to improve performance and without like running a long fine-tuning process. We can just use some group lasso and learn like logistic regression on all features of our neural network. Of course, there are like some difficulties when we have 3D features. So they consider like cases where you can adjust this high dimensionality of the features. And they show that it helps a lot in transfer learning tasks. And it's much easier like computationally than like fine-tuning model. That's all for this slide.
It's amazing.
I don't want to say that. Thanks, Alex. No, this is just pretty interesting.
Yeah, that's fine. Like there's like a lot of papers on like multi-objective optimizations. This like another one. I think this compared to other one, it's not trying to solve like just by directing gradients, but it adds additional like reference points that you can use to guide your optimization. So I think like the main contribution of this paper is having like this reference point to direct your optimization process in multi-objective scenario. That's all for the slide. So there is like self-supervised representation learning paper that creates a Latin graph and defines like self-supervision on nodes and a graph level. And I think the main interesting part that they create a graph that like in Latin space.
That's
and I think, yeah, and it's more like related to SMAN. I think it's also related to the like undersampling. That, for example, if you have different sampling rates of the data, we can create like a graph in Latin space, but that is invariant to sampling rate. That's all for this slide.
Yeah, that's interesting. Thanks for bringing it up. See.
So there is some work like on lottery tickets. I found like a lot of papers like this, and this is more like related to Reasat. The claims here like very big, but like I didn't understood like exactly. But they say that they can find like lottery tickets in like sparsity levels of like 30%. And they do like some computational tricks to make it like easier to find this lottery tickets. That's most like about this paper. It's more like
Sorry, go
it's
ahead.
more like they trying to like they solving like two problems like computational efficiency and they show like kind of lottery tickets in sparse scenario. I think this is the main contribution.
They're losing in performance as well, right? All of them.
Yeah, you can see that I think on different levels sparsity you do lose like accuracy, but maybe like till 60, like some models work. Like sparsity 60, you lose like a bit more than 1%. So like I don't know like related works that I can compare with, but I think it should be interesting to reassess more.
Yeah. You said would know some of them.
Yeah, so this paper is interesting to me, like because it explores like invariance to time scaling, and I think it's related to like time series, and I think sometimes scale will be like important, and some models won't be like robust as the scale of the time series, and this kind of like they motivated by like nearer data of the cells, and they trying to make convolutional neural network to be invariant to the time scale, and they show that like it works better than just temporal convolutional network, and it's robust to multiple scales, and if you use like multiple training scales during training, you can improve your performance.
What about the CTC laws, the connectionist temporal classification? It's already solved that problem, right? Back in Alex Graves' thesis. What was it?
Yeah. Yeah, I don't know like details.
Why are they not? Why are they like reinventing the wheel? There might be a reason, but you know, do they even cite Alex's work? CTC.
Actually, not sure because they didn't talk about CTC.
Yeah, but you remember, right? CTC is
I do know CTC, yes. Like there is also like dynamic time wrapping, but like probably like there is missing connection how like you can relate dynamic time wrapping or CTC with this. I think this is more like architectural solution rather than like optimization. So like I'm not sure how like they compared. I don't think they have this result. They probably just compare temporal convolutional network to like regular typical vanilla layer, then like doing like
yeah, okay, well,
function.
that's interesting. That they kind of, it feels like porting the results from LSTMs now to CNNs or something like that. Why not just
I think it's like more like in general invariance, like equivariance is interesting because if you don't want like to use like data augmentation for each like property, instead we can just use invariant or equivariant like group invariant transformation that kind of more efficient and like just running data augmentation. Like well, simple case when we have rotation like in 3-dimensional space, if you rotate, like it grows like exponentially with the dimensionality of the input data. So you might use like rotation invariant layers and reduce your computation time, reduce your augmentation.
Well, thinking about this equivariance or invariance to everything possible shows me that algorithms, or AI, if you will, can be much better than humans because we have our limits as well. Like if the speech is too slow, we won't perceive it. If it's too fast, we won't perceive it. There is like a window, and it's not totally invariant to stretches and things like that. And the cow from the meme channel as well. If there are two cows, you know, for the 6 meter cow, whatever the Dashkan has posted, if the cows were too close, even if they were unrealistic, but still kind of realistic, no human would detect that those are two cows. We would also kind of, okay, throw it into one cow. When it's too big, only then, okay, invariance fails us, and we know now it's unrealistic. So just, but the algorithms can be, you know, well, the cow length invariant algorithm could be wrong, right? It could assign that 5 meter cow to a cow when it is not a cow. Just throwing thought out there, but yes, interesting. Next, or staying on this?
Yes, and next. So this is more like towards invertible neural networks. If you know, like NICE or real MVP, this is like butterfly layer that they introduced to like preserve like layers of the network to be invertible. And this is basically a small trick that is kind of new, how you can make your network is invertible. I think it's more related to NICE or real MVP papers. So it's just different way of partitioning the features in the layers. Yeah, that's it.
Sergey stepped up for a second. This one. There you go.
Yeah, so there is an OpenAI paper, it's called Glide, and basically Glide is about generating photorealistic images, and you give like text description what you want to generate, and this is basically related to DALL-E 2, and they use like diffusion models here, and they like in their presentation they explain well like building blocks like diffusion model and how like you can guide diffusion model generation with classifier and without classifier, and I think this is just interesting to read, just to understand how like DALL-E 2 works, and the result kind of impressive.
Yeah, so TJ comments that Glide was the basis for DALL-E 2.
Yeah.
And TJ will be talking about all of that. So in the same meeting in this week.
Right now.
Yeah, so there is like some structure preserving guns. It's also like related to invariance and group invariance and equivariance. So like for some data, like when you generate, like some images can be like like could be the same, but they can be rotated. So if you want like to increase efficiency of the GAN models by saying like kind of constraining like or improving GAN to like use the capacity of the GAN on meaningful stuff rather than like generating rotation. So and I thought about like if they can use like GAN that will be bounded by structure, what if we can just generate brains with GAN, but guided by structure of like based on segmentation. And also we can include these invariances that common to medical imaging data to generate GAN images of the brain. And in this way, we can improve like data efficiency, like in solve like some, like simplify life to GAN, so the GAN can focus on what we want rather than focusing on generating different rotations. That's all for this one.
So they're on this one, they're like trying to be equivariant to rotations, you said?
Yeah, so like rotation translation, there is like rotor reflection, but they do like on this pathology data, so.
Okay. Yeah, that would be really useful for like if you want to have like your MRIs classify tumors correctly from different, but you only have a few tumors and stuff.
But it's more like I think it's a new like area where everyone wants to do equivariance and variance to group transformations, and they want to put this building block to previous models. So I think this is just explains why we can see these papers and what they can and what they trying to solve.
Yeah. That's the reason I asked like what they were trying to be equivariant to, because like I first saw that they were being equivariant, but like if you don't specify what you're being equivariant to, it's kind of just like a buzzword. So.
Yeah, so this is like work from Microsoft, and they introduce this deep speed mixture of experts, and they basically trying to, like their research group trying to improve training costs, like reduce training costs and like reduce the number of parameters in the model, and in the same time they want to increase the performance of the models like GPT. And I think this paper is interesting in the sense that they like can train a model with billions of parameters and like reduce inference latency, training through output, and reduce the model size in the same time while preserving the performance of much bigger models and much more computationally expensive models. And they have like a library called DeepSpeed that can be used on top of PyTorch. And they also like share specific these layers, like mixture of experts, which you can use to like train big models. So I think this is like why this paper was interesting for me. I think that's all for this time. Yeah, so there are like some self-supervision work for video transformers. It's more like related to our self-supervised research for time series. In the main contribution of this, they use video transformer, and they add like 3 different losses that kind of helps to improve performance overall of the pre-training. And they have like task classifier, they have tasks that predicts temporal order of each frame, and there is the attention model that predicts temporal flow direction. So it's more like combination of like self-supervised objectives that put together to improve performance. So I don't think like like it's very interesting to have fun, but it's just to see how we can improve our whole milk architecture. And I think probably like a lot of this like related to whole milk or like the beta models that Osman proposed. So that's all for this slide.
This is related to the stuff Capella is working on as well. So the video transform, I'm not familiar, but it's just a 3D vision transformer, right?
Not really. There are like different architectures. I think they have like, so I know the popular one is called, I think, Timesformer, and they do separate spatial and separate temporal attention. And there have been like maybe 5 types of attention you can use to deal with spatial temporal data. And I think the most effective was separate spatial and separate temporal. So I think it's, I think you can find it, and like there are multiple questions like efficiency and performance, I think.
I will share the slides and the detail of the channel. So
We can go to the next slide. Yeah. So there is a paper on understanding the robustness of vision transformers. I think it's from NVIDIA, and they talking about how like self-attention related to information bottleneck, visual grouping, and robust generalization. They compare self-attention to spectral clustering, and basically they're trying to explain how vision transformer works. So I think that's all for the slide.
Where does the information bottleneck pop up here? Can you go back?
So they related. I didn't go through paper yet, but it's from their slides. And
Okay.
I found it's interesting read because they kind of relate self-attention to everything. So this is self-supervised learning, and basically in common contrastive learning framework, you have 2 views, and each view has like different data augmentation. Here they're using like augmentation like that basically creates a mask. So you have like separate second models that like tries to learn to mask the image on different paths, and then you mask one view and perform like your contrastive learning or self-supervised learning. And basically the main novelty is like learnable masking function. So during training of your self-supervised model, you also learn the models that generate mask. So I think this is like the main novelty, and overall, I think it improves previous self-supervised baselines by 3%. So it's like model agnostic
An interesting interpretability as well. You can output the most sort of adversarial mask for a given class, you know, masks it up.
Yeah, it's interesting. I think like even like we can use it like for learning representation of the brain by masking like some parts of the brain, and it's more like spatial semantic, like semantic dropout, but also like semantic data augmentation. I don't think like we need to train another model, but we can train like meshnet that generates mask, and we just based on Atlas, like which we have like 104 classes, we just mask each like region and generate additional view, and your model will try to relate it. So I think that's all for this slide. Yeah, so so this work is about like trying to unify all possible tasks like your model can do, and like different modalities like text, image, video, speech. This is like common direction of research like in big companies like Google, for example. And I think this paper was from some Chinese lab. I might mistake here, but so I found this interesting because this was a big research direction where you have like any kind of modality, any kind of input, but you have like one universal architecture that can do any task you want by fine-tuning. So you learn like kind of big universal model to any kind of data, and then your model can do any task. So that's all for this slide. So this is like more like small, simple trick. It's about training neural networks. And when we train like neural network, we have learning rate. If you set too high or like too low, your model like tend to learn or not to learn. And especially if you have like noisy data, your network might overfit to the noise of your data, and they demonstrate that, for example, they have this car image and they put like this patch, and depends on learning rate, you might overfit to the patch or learn meaningful representation of the car. And they say that your layers in neural network can be like slow or fast. Like, for example, fast should be the last classification layer, but the layers inside should be slow. And then basically each layer can have like different learning rate. And this way you can kind of improve your performance of your model. And also you can help like improve your transfer learning performance by using different learning rate for your layers. So like, it's more like you have case like for transfer learning where you freeze the weights and you unfreeze the weights. But here you're also adding like more like multi-rate learning rate to each layer. So each layer can adjust faster or slowly based on the task. For example, we expect that first layers of the network might need like less adjustment than like last convolution layer. So I don't think like it's something new, but maybe they just explained it well. But I think it's interesting to check just for additional skill set. Yeah. Yeah, I think I also have to leave. But I like in these slides, I basically added some slides that I didn't have time to check. But I found like there are a lot of papers that talk about how like neural network works, and I think if you just move to other slides, you can see there are multiple techniques about like assemble models, or this paper, for example, just says if you have different models that you train with different high parameters, you can just take average of this trained networks, and this average of your trained weights will perform better than assemble or your single model. And they call it model soup.
So how many more slides do you have? We're kind of out of time, but we can.
I think we can skip. But like it's just mostly like you can just slide through, and maybe people can check. Like there are many like interesting like papers I haven't checked yet. Mostly like I want to point like on differentiable top K classification learning, or there is a differential nearest neighbor. So it's more like how you can take previous machine learning algorithms and make them differentiable that will work end to end within your neural network. There are a lot of stuff like tricks on mix-up. There are deep equilibrium networks that there is a fixed point iteration project with Sergey. And there are a lot of papers that explaining, for example, optimization, like momentum in stochastic gradient descent, or other optimization methods. There is a lot of work on auto distribution, and there is still works that exploring shallow and wide neural networks. Like, that's all.
Okay. Well,
Thank you, guys.
yeah, thank you, everyone. We're out of time, so we'll maybe discuss them offline, all of those folks and papers. But thanks for preparing that.